Okay. Thanks, William. Okay, so today, William asked me to come and talk about hardware verification work that I've been doing at UBC over the past several years. And I will. Now, quite a bit of the recent work I've been doing has been built upon. Oh, it's not on? It's on. The green light's on, yeah. Okay. Do I need to speak loud enough so they can hear me off in network land? No. Okay. So quite a bit of this has been based on an integration of the Z3 SMT solver into the ACL2 theorem prover, which is the PhD thesis of Yan Peng, who's here today. Yeah, there we go. But I've also done some other things too. So I'm going to spend a lot of time on that because I gather also from the work that's been done here that kind of cool things you can do with theorem proving, even though my impression is that ACL2 isn't the mainstream theorem prover here, will be of interest. Okay, so what do we want to do? We want to use ACL2 because, well, pick your favorite theorem prover and you get recursion, induction, a rich set of data structures, all kinds of capabilities for proof management and all this other kind of good stuff. Because oftentimes the things we want to prove are more than you can do in just one push button run of something. But the big complaint about that approach is that, yes, it's great, you can prove really big systems, but you can spend weeks trying to guide the theorem prover a step at a time through some really, really tedious details. And then you say, but SMT solvers are wonderful because they give you SAT, mixed literature into your programming. Z3 even gives us the cylindrical algebraic decomposition algorithm for solving systems of equalities and inequalities over rational functions. You get arrays, other kind of stuff like that. So the dream, which has been here for quite a while, is can we cut out a whole lot of the tedium of theorem proving by tossing in an SMT solver? And we're certainly not the first people to try this. So I'm going to start off with a motivational tale to kind of say how we got to where we are. But then the big picture this is going to be that what we have found in doing this is that what we're getting in ACL2 is that it gives us reflection and metaprogramming. What the big win that comes from reflection and metaprogramming is that typically the goal the user wants to prove doesn't look like the term you want to throw at the SMT solver. And so you can either go through a lot of work to massage your goal until you finally have something that's all expressed explicitly in terms of the SMT solver, or we say, but hey, programmers and proving people follow common idioms. What if we just recognize the common idioms and we can just zip through this and we can take a goal written the way the user wanted and turn it into the goal that the SMT solver wants. So that's going to be the big picture, but we'll start off with this. So the motivational tale was I was working on the verification of analog and mixed signal circuits. And kind of a great example of such a circuit is what's called a digital phase lock loop. And the goal of this is that we have some reference oscillator, phi ref. We're going to create our own version of that oscillator, which is set to be at n times. There we go, where's our n? There we go, it's set to be n times the frequency of the reference, and also with a fixed phase relationship. And these get used for clock generation, for linking up high-speed serial links, like between your computer and DDR memory, and all kinds of other places. But, and by the way, once the thing is actually locked up, then you have a beautiful linear system. And so you can just use standard linear systems analysis and you can answer all kinds of questions about that. And if you talk to a typical phase lock loop designer, they will speak linear systems theory to you all the time. Right? They've got that stuff down really solid. It's a beautiful, clean mathematical formulation for things. But what happens when you're not in that locked situation? And we get there a lot. When you turn the thing on, it's not necessarily what it's supposed to be. But now we try to do all this energy management and we change the operating voltage and clock frequencies and things rather frequently. And so now what you do is you've tossed yourself someplace a long ways from where it's supposed to be. Does it get to the right place? That's the convergence problem. And the convergence problem, you have to take into account that these circuits really are nonlinear in the large scale. The terrifying thought for the typical analog designer is, what if there is some place you can get stuck that isn't the place you're supposed to be? So that's the global convergence problem. Can we show that you always get to the right place? Now, so we took a look at this, and one of my former students in her master's thesis took a look at this design and proved the convergence property using SpaceX, but actually what she did, she proved about 30 different reachability results with SpaceX. And then said, and so now we can examine those and we can cobble them all together and we can show that we've proven the thing. And it has fixed design parameters. So we said we proved it for one specific set of parameters for all of our devices and components. So Jan took an interest in this, and she said, you know, I can take that model that you have, and I can use the Riccati equation to get a candidate Lyapunov function for this. And then what I can do is I can just hand that to Z3 and say, does this Lyapunov function, this proposed function, satisfy the right properties to guarantee global convergence? And she said, look, I can just type in this function. I ask Z3, and it says, yep, you're good. Cool. Now, she did this on a highly simplified model. So we said, can we back this? Can we take a baby step towards the thing that designers would really use? The answer is yes. Can you take 2 baby steps? No. And why can't you? Because when we're looking at the nonlinear system solver, it's actually running, an exponential cliff was an understatement. Cylindrical algebraic decomposition has non-elementary complexity. So its worst case complexity is a 2 to the 2 to the 2 to the stack of 2s, the height of the size of the formula. Now, they do a bunch of heuristics to hopefully not hit that most of the time, but still, just a slight change turns the problem from being solved in a few seconds to taking multiple times the lifetime of the universe. So we want to do something else. So we said, okay, what if we could break this problem into pieces and cobble the pieces together? Well, we need a theorem prover for that. So what we do is you take a look at a manual proof for the fully parameterized model involves a recurrence, which is basically a sum over geometric sequences and things like that, and a clever rearrangement of the sum and gives you a key inequality. And then a bunch of tedious algebra completes the proof. And so what SMT 1.0 did is we said, okay, so we have the original goal, and we add some more assumptions, which are basically facts we've already established, but Z3 doesn't know about. And so we say, and what we did is we said, so if we can prove that our goal is translated to Z3 and the assumptions that we made imply the original goal, and if you can prove these 2 things, so in Z3 we prove that our assumptions imply our goal, and then you can conclude the goal. And so it worked. Good. So that was really cool. So we actually tried this. We could prove the main things about it. We're really happy. And of course, the other recurring theme in this talk is going to be whenever we can successfully verify something, we try to verify something bigger. Right? And of course, if you do that, that means you constantly bump yourself into scalability issues. So sure, this worked. And so what's the scalability issue as you try bigger things? Well, it's that we handed this goal back to say that the new assumptions that we made and the result we proved in Z3 taken together imply the original goal. Well, it turns out that you'd think this was straightforward, but you hand it to ACL2, and its rewriter can turn everything into a big pile of spaghetti, and it says, now I'm totally lost. And so as we try bigger things, this fails. So what's the next step? We say, well, it's kind of crazy that the rewriter is trying to reconstruct what we've already done because we know how we got there. So what we'll do instead is we say ACL2 has comprehensive support for metaprogramming. So what we can do is we can do correct by construction transformations of our clause. So rather than just flattening everything out and then asking, is it the same? We can do a whole series of, we'll take this step, and we know that we've preserved soundness. We take another step, we know we've preserved soundness. We take a handful of steps and we say, now we have something that the SMT solver can handle, and we know it implies we know that proving that implies our original goal. We know we have we've only weakened our hypotheses as we go along, so strengthened our claim. And so now what we do is we make sure that we only return things to ACL2 that are small enough that they go through quickly. And how do we know that they're small enough? 2 things. One is you just do quick, informal, big O reasoning to say, did I make anything bigger than it has to be? Right. And can I guarantee that if I sort of decompose my problem nicely, that all the pieces I hand back to ACL2 are also similar small pieces? So big O reasoning helps us a lot. And then the other thing is you try real proofs and you find out where it hangs. You come back and attack it. And so we're making ongoing improvements to the user interface. Okay, so that's why we're doing this. So how do we actually do it? Well, you start a goal, and what we do is that we take advantage of this combination. There's this kind of way of tossing the potato back and forth in ACL2 that goes between the idea that it has what are called clause processors and what it calls computed hints. The basic rule is that a computed hint examines the current goal and can tell the proof engine, hey, try doing this. And now the nice thing about hints to the proof engine is that they have no impact on soundness. So they can be guidance, but we haven't changed the underlying mechanisms of the proof engine. So a computed hint can do anything. It can make any hint it likes, and we don't affect the soundness of the argument. Of course, now if you give stupid hints, you can cause the theorem prover to never prove it, but you can never cause the soundness issue. And then the clause processor, we can have these verified clause processors, which is what we use for the most part, which replaces a clause with 0 or more other clauses. So we develop a proof within ACL2 that says that if we run an evaluator over the replacement clause, it implies and that implies the outcome of running the evaluator over the original clause, which says that so if I can prove that the replacement clause is a theorem, then the original clause must be as well. Because that proof exists in the meta logic of ACL2, we don't have to do that on the fly when we run things. So we can say, now you just run this piece of Lisp code. You've done the transformation, and it's good and safe. The other somewhat scary thing that comes up, so the basic strategy is you take a goal, you bounce it back and forth to do all these transformations, and now at the end of this whole process, we now have something that is written entirely in terms of things that the SMT solver understands. That's good. Now, how do we get from there to Z3? And I will explain this in just a moment. We do something heretical. So at this moment, heresy comes in. We use what is called a trusted clause processor. And so it just transliterates the goal from the common Lisp representation to Z3's Python API. And we don't prove that that's correct. And you say, well, why don't you prove it's correct? Well, because we don't have an ACL2 representation of Python. Not that, I mean, who could, right? Which is, we're running the API, we don't have the full ACL2 representation of what the SMT solver does. So we just hand it through there. And so there's no correctness proof. We just say, if this thing tells us that the formula we just gave it is a theorem, then we will accept that that's a theorem. So we're trusting Z3. We're trusting our translation process. Now, what happens is that to do that, you have to add what's called a trust tag. And that becomes a hypothesis to any theorem that uses this, or any theorem that transitively depends upon it. So if you now want to put your logician's hat on, what you just said, we just added soundness of this trusted clause processor as a hypothesis to our proof. And then your whole logical world holds together again. So yeah, we can make a simple soundness argument through the whole thing. Yeah. So, and the basic soundness argument says that, well, ACL2 is in first order logic, so if something is not a theorem, there must be a model for a counterexample. What we do is we say there must be a model in the logic of ACL2. We show that we can construct a model in the logic of the SMT solver. And so if the SMT solver says that no such model exists, then we know that no model existed in the ACL2 world when we're done. Okay. Now, there's a handful of technical issues, and I think to keep the time reasonable, we'll go through there. I'll only come back to these if somebody asks. Biggest gaps are that ACL2, like most theorem provers, like Coq, like Hall, works in an untyped logic. And the SMT solvers work in many sorted logics. So what we have to do is we have to assign types to all of our variables. And we have to make sure that we haven't over-restricted things in that process. So we can do that. And then, And then the other thing that we have to do is that ACL2, now there is ACL2R which has real numbers, but most work people do is in ACL2 which has rational numbers and Z3 is reasons about real numbers. And so now you get the things, for example, in ACL2 we can prove that given any rational number x, x times x is not equal to 2. And yeah, that's not a hard proof. You know, there's a proof by Pythagoras that does this, right? And we can do the same proof ourselves. Okay, now our translation into Z3 will convert the rational to a real. It will fail to give this as a counterexample. It's not a valid counterexample. So what we get is that, and basically what we get is that soundness is preserved because in this case the set of possible models in Z3 is a superset of those in ACL2. So we may find a model for a counterexample which isn't a valid model. And that means that Smtlink may fail to prove a valid theorem, so it's incomplete. But we're not going to prove a non-theorem. It's, so in that sense, it's sound. Now, part of that relies on the fact that we do not translate quantifier functions like for all and exist, because you see, you could try to state the theorem that there exists in x times x equals 2, and Z3 will say, fine, here's an example. But of course, it's not a rational number. So when you look at that rational justification, I'm an engineer, so I say, yep, that's fine. And we're working with Matt Kaufman, the main code developer for ACL2. He's a mathematician, and he says that's not quite cool. So, he says it's not quite cool. You know, you can have non-standard values, and you can have this and this, and you know, you can get from rationals to reals with the real field extension theorem. But now you need a submodel, and I don't know. All right, okay. So, Yen wants to graduate. I'm sure she'll have a proof. There we go. Good, that satisfies Matt. Okay, what about proof reconstruction? So I say this is an orthogonal issue. So I know that most of the world has gone for proof reconstruction. Now, in principle, the final trusted clause processor could be replaced with a verified clause processor that does proof reconstruction. Right? Okay, so why don't we do that? Because in the scope of a really smart grad student and a not quite so smart faculty member working on this project together, what you get is you say, well, there's only so many things you can take on. And so many people have taken on proof reconstruction. We say, no, we're going to take on making this useful. We're going to take on how we get the real kinds of theorem statements that people have and turn them into things that we can really prove with our theorem prover. And if somebody wants to come around and say, I want to do proof reconstruction, that's great. I mean, we'll also note that proof reconstruction is oftentimes really slow. So you could say, yeah, you can run 100 times slower. For problems that already take a while, we say, well, that's not quite so interesting. And finally, proof reconstruction limits what you're able to do. You say, I can only put in a decision procedure if I can figure out a reconstruction procedure for it. And so it hinders experimentation. Now, so what I'm going to notice is that a property that never gets verified, like, what happens if this pivot tube fails, right? Okay, is in many cases a much bigger risk than a property that was verified even though we trusted this big pile of code like the SMT solver. Right? So now, I fully accept that there are places where the reliability requirements are so high that you'll say, no, I have to boil this all down to a very small set of axioms or I'm not going to trust it. And so in that case, fine, go for proof reconstruction. But I'm going to argue, if we get to the point that we're actually verifying a whole lot of things that you wouldn't verify otherwise, with the caveat that we are trusting the SMT solver, we see that a lot of people verify things trusting SAT solvers and SMT solvers. Every chip today that gets fabricated basically has gone through a SAT solver that nobody proved correct. Right? We wouldn't get chips out to the fab if we had to prove our SAT solvers correct first. And our chips wouldn't work if we weren't using those SAT solvers. So, in that combination, it's a pragmatic trade-off. Okay, so now that we've looked at our architecture and soundness, I'm going to give an example of how we're doing all this reflection stuff with types, because that's one of the biggest ones. So, so ACL2 is untyped, kind of. Yeah, I mean, if you take a look at it, yes, it's a theorem prover for untyped first-order logic, right? So it's untyped. But users write theorems and functions that are very clearly typed. We have type recognizer. We have Lisp type recognizers like Boolean P or cons P. And users can write recognizers for their own types. So if you actually look at real stuff that real people write, you see all kinds of types all over the place, very clearly described. So in Smtlink 2.0, we support a set of built-in types, and we translate. There's a package in ACL2 from the community called FTY, which introduces a wide range of types: list, a list, product types, sum. So basically, a whole set of algebraic types and a handful of other things. And so we handle translating all those into their corresponding Z3 types. Now, one of the slightly uncomfortable things here, which was done to get a prototype, we trust that FTY package. So that FTY package says, this thing is a product type. We go, yep, I believe you, right? So in the current version, the type inference will be done with one of these verified clause processors, and we'll make it independent of FTY. And so basically what you can do is you can say, I have a list type, and my list type has this recognizer integer list p. It has a fixing function, integer list fix. It has its own char, cons, coulter, and nil functions. And then you could say, good. And we can tell our trusted clause processor that that collection of 6 functions defines a list. And it says, OK, fine. I'll translate that into Z3 defining a list. But I know the axioms for a Z3 algebraic data type. And so what I'll do is that I will then return the subgoals that say, the thing you gave me for integer list cons looks like, behaves the way I expect this algebraic data type in Z3 to behave. So we basically return our axioms for the Z3 types as subgoals to ACL2, which, if you've already proven the right theorems about your functions, just go right on through. OK, so what we are going to do is we're going to support F2Y, and in fact, automatically put all those theorems together for you, and automatically create the specialized versions of char, cons, and coulter, automatically do the translation, so that all that happens under the hood for the user, but then we don't trust anything extra in the process, other than that we trust Z3's way of representing algebraic data types. OK, so yeah, one of the things we observed is that types can be tricky, so that's why we have to do all this stuff. So I can define this integer list, and here it is in Z3. Now, in ACL2, char of nil is nil, right? I mean, you just look char of nil, of course you see nil, right? Now, if I do this in Z3, integer list.char of integer list.nil is integer valued. It's otherwise unconstrained, so Z3 says it's some integer. And in fact, you can write problems. And now, of course, once it chooses an integer, it's stacked for any occurrence of integer list.nil in your formula, because, of course, integer list.nil is a function. Char is a function, so you must return something for nil, but it returns an integer. So now that you know this, if you do a direct translation, you can state something which is not a theorem in ACL2 and is a theorem in Z3, right? And so you can prove a non-theorem in ACL2. Which is rather convenient, because then, of course, you can prove that false is a theorem, and then all your other verification headaches go away. But we don't want to do that. So currently, Smtlink 2.0 recognizes these places, and what we do is that it returns a subgoal to prove that that all of your translations are sound. So it basically says, if you take a char of something, it better be non-nil. It better be a cons phi. Discharging these can become a bottleneck, especially if the goal has become huge after all of our function expansion and all this other kind of stuff. So now what you do is we can now take a goal, and we can do a bunch of translation work, which goes really, really fast, and we toss it into Z3, and Z3 discharges it, and that's really, really fast, and then it comes back and says, are all your cars good? And then you go to lunch, right? Wait for that. So we're noting that. So So we note that the problem is that functions like cons, char, and coulter are polymorphic in ACL2, but in Z3 we need specific versions. So in Smtlink 2.0, the user wraps terms with fixing functions to let the trusted clause processor know which one to use. It works, but it's cluttering, and discharging the subgoals that it produces can be a bottleneck. So what we're going to do is just use reflection and metaprogramming so that you can build your own type inference engine, figure out what all the types are, figure out that it's safe to apply the fixing, that applying the fixing function doesn't change the meaning of the term, and all these kinds of things, and then we can do that. That runs very, very fast. And then we get rid of this problem. OK. So having now said how wonderful it is to use clause processors in metaprogramming, and having kind of promoted that all through here, it's probably time to say something about what really is a clause processor. So a clause processor operates on a quoted term. So it operates on the Lisp syntax for a term. And we can introduce an evaluator for those quoted terms. And now, this is a little bit of magic that we're doing, because of course ACL2 is first order, right? So how do we get an evaluator for something? And it says, well, what you can do is you can define an evaluator for any fixed set of functions, right? So, right, the problem is you can't have things like definite and stuff like that, or lambda, and evaluate them suitably in a first order theorem prover. Well, that's okay, right? So we just given some fixed set of functions, we can define an evaluator that works over those. And then what do you do about anything else? Well, it says anything else, then any term whose top level function is something other than one of those, then its meaning is whatever ACL2 says it is. And that's this notion of having, you'll see throughout all this, I'll talk about having my-eval. And my-eval is that we've constructed this evaluator over some limited set of functions. This is how we dodge we're in a first order world problem. Okay, so a clause is a list of such quoted terms, and the evaluation of a clause is basically the disjunction of the evaluation of each quoted term. And a clause processor returns a list of clauses whose evaluation is the conjunction of those. So basically, ACL2 pending proofs are in conjunctive normal form. And in any environment, the result of evaluating the list of clauses returned by the clause processor must imply the result of evaluating the original clause. Okay, so that's the proof you have to make, and those are the proofs that we get. By the way, one of the things that means is that if a clause processor returns an empty list, it's discharged the goal. It says that nothing is sufficient to imply the original goal. Or it can return multiple set goals. And so a verified clause processor, this implication is proven within ACL2. So we just proved that these syntactic manipulations of clauses preserve implication under the logic of ACL2. And so now that you've proven that, now you have this list function that can just be run directly on the clause. That's what we're doing through all this. Okay. And the really awesome thing is that a clause processor can use previously established facts in the logical world. So what if I write some function to take the sum of the elements of an integer list? Looks like this. And now how can we translate the body of sum into an SMT formula? Well, we note that using reflection, we can pull out that sum of x is the same as this. And so it could just ask the ACL2, it just asks ACL2, what's the definition of sum? And it says, this is a fact. And so this fact is returned by this thing called meta-extract. And so for any such fact, the evaluation of fact is logically true for any valid evaluator. And so we can always add not fact to the list of disjuncts, and we can perform verified simplifications using these facts. So what does that let us do? So from this, we can take the fact that it just gave us, and we can put in a if integer p list of p, the fact must be true. Because of course, if fact is true, then if p fact t is true, no matter what p is, right, we can put any antecedent on true we want. And now constructing path conditions and using meta-extract, we can now work this down to we can figure out the types of all the terms that were underneath there. And then we can say, okay, so I figured out that x must be an integer list, and so therefore the nil that you were comparing with must have been integer list nil. I could figure out that x was an integer list, and so therefore the car you meant is integer list car, and the cooter you meant is integer list cooter. And so it says, yeah, I can deduce all this type information. I can put in the type specific versions, and hey, this goes right to Z3. And this was done all syntactically, so we weren't running the major proof engine to get any of this done, so it's fast. Okay, so then the clause processor can then look for existing hypotheses in our clause that establish integer list p, and with that, then we do the other simplification, and that's the thing that we can then apply to our transliteration. Okay, so summarizing types. ACL2 is untyped, but users imply a rich set of type recognizers. A verified clause processor can do type inference, and so we can support a rich set of types and users can use them. So that's my that's the example where I've walked through all the steps of how we're using metaprogramming to be able to simplify proofs. We do it in a bunch of other things too, but I know I've been kind of zooming through that. Any questions about metaprogramming types, all that kind of stuff? Yes?
Sum type.
What's that?
The definition of sum, if you export that to Z3, it was kind of recursive. How does
Oh, yes. Perfect. Oh. You know, I often tell my students I pay for good questions, but right now I believe all the change in my pocket is Canadian. There you go, but okay, awesome, right? So it's a fantastic question because it leads exactly to what we're going to do with functions, right? And so what happens with functions is that basically, so you're right, Z3 doesn't have recursion. And actually that's really important. When I mentioned that, you know, that Matt said, but what about when you combine all these things? When we've discussed it, apparently the big saving grace in this is that there's no recursion, which means that we don't have to worry about some function that's trying to walk down some non-standard list or something like that and make crazy things happen. So what happens is that so in our approach, every function in ACL2, any user-defined function, gets translated into an uninterpreted function in Z3. And we just emit suitable constraints. And in fact, I'm going to give an example of how we can do this. So yes, I can take sum, and I can just say that sum is an uninterpreted function. But I can take particular instances of sum that appear in my current formula, and I can tell you how they expand. Now, obviously, if it's a recursive function, I can never expand it all the way. But the cool thing is oftentimes you don't need to expand forever. Sometimes just a few expansions work really well. And in fact, so recursive functions are translated into uninterpreted functions. And one of the big lessons we've learned is don't beta reduce. Beta reduce will make your life terrible, right? See, there's a simple temptation to say, I see this function, I need to know more about it. Why don't I just replace this function call with this body with the right substitution, right? I could do that. It's easy. It's really, really easy. No, no, no. Leave the uninterpreted function where it was and add a new hypothesis that this instance of the uninterpreted function is equal to its body. That's equally safe. And we'll see why in just a moment. So the first thing it does is it avoids exponential blowups in the size of the formula. So I can write examples where if I didn't do these substitutions as I go along, or if I didn't introduce fresh variables and things like that, that I can make an expanded term which is exponentially larger than the original. That goes against our big O rule of don't do anything that's big O bad, right? It also, but what the really cool thing is it makes it much easier to discharge goals under an induction proof. So let's do an example of this. So what I can do is, so let's say that I define this function for taking the sum of the first n natural numbers. Okay, pretty easy function, right? So n's a natural number. If n is 0, then we return 0, and otherwise we take the sum of n plus the sum of the nats up to n minus 1. Okay, and so now what I want to do is I want to prove that if n is a natural number, remember ACL2 is untyped, so even though I had said in my argument it's a natural number, my statements have to hold no matter what type n is. So I'm going to say if n is a natural number, then applying sum of nats to n produces the same value as this formula. And that's just the usual textbook formula for doing this, right? And we know okay. Now, so this theorem is easily proven in ACL2 without using Smtlink. I mean, we could just take the theorem and the proof goes through. But that's not fun, right? And actually, the reason for doing this is because if I give you an example that's big enough that we really need Smtlink, then of course I'll fill up a whole lot of slides with it. So we'll do the simple one. Now what we do is that, so the interesting part is that ACL2 will look at this and it will attempt to prove that goal by rewriting, and it will figure out that it can't, and it'll say perhaps I can use induction, and it says sum of nats is a recursive function. There's a corresponding induction scheme. It sets up the induction, and out comes this. Okay, good. Now, what would happen if I did beta reduction on these two? So notice that this is a formula which is relating sum of nats of n to sum of nats of n minus 1. So what would happen if I did a beta reduction? Oh, I would get a formula that would relate sum of nats of n minus 1 to sum of nats of n minus 2. Equally useless. But what if instead I make sum of nats uninterpreted and add constraints about what sum of nats of n is and sum of nats of n minus 1 to their respective instantiations? Then it finds out that there's this, then Z3 gets told, oh, there's a relationship between sum of nats of n and sum of nats of n minus 1, which is the essential thing for discharging the goal. It will also find out that there's a relationship between some of nats of n minus 1 and some of nats of n minus 2, which is totally useless. But that's okay, right? Just disregards that, and we go on. And then the proof goes through. So, describing function instantiation, so one of the things we've learned in this, describe recursive functions as uninterpreted functions, and describe function instantiation as stating equality relations between the particular instance of the function and its expanded body. Don't rewrite it and replace it in place. Okay. And so that allows the SMT solver to, in some sense, to see more of the problem, to see the essential parts of it. And especially because proofs tend to involve lots of recursion, we want to make it so that our translation plays friendly with recursion. An induction. Any questions on that? Did that get at your question as to how we translate, how we handle a recursive function?
Yes, it sounds like you're doing the induction in ACL2. Right?
That we're doing what?
The induction is done in ACL2. So
Absolutely. Right. And in fact, this is one of the great reasons to do this. You see, you know, Z3 is great for discharging big, messy formulas, but it can't deal with induction. Well, you know, a little bit. I mean, there have been some papers out basically saying, well, what I can do is I can write a recursive function and send it through the verified C compiler to generate Z3 proof obligations and run them through there. And basically, yes, I can write the recursive function that corresponds to the induction I want. Yeah, you can. And I say, yeah, you could do this, and it's kind of a roundabout approach. Or I can say, I can just write the inductive proof claim I want in ACL2. ACL2 sets up the induction, and then the induction step is a great candidate for discharging with the SMT solver.
Next question then will be, so when you send this to Z3, how do you know what facts about things to give it? Like,
how do I know? Oh, right. How do I know what facts to give it? Oh, fantastic question as well. Are you going to run me out of chain? Yeah, okay. Yeah, okay. Yeah, there you go. Yeah. So how do we know which facts to give it? That's because one of the cool things that SMT-Link does is that SMT-Link itself can take hints. And so one of the things we allow is there's the hypothesize hint, which says, add the following hypotheses to the goal. And what of course happens is that those hypothesized hints get returned to subgoals for ACL2. Now, generally what you hypothesize is some instantiation of an existing theorem. In fact, Jan has promised me that it won't be long until one of my hypotheses can just be instance of particular theorem and binding a variable so that I don't have to state the instantiated theorem and then say, hey, it's this theorem, right? So what that does is it gives you a very controlled introduction of facts. I did this with a cool thing. One of my former students is working on reasoning about convex functions, and first he had to formalize real vector spaces, and he needed the Cauchy-Schwarz lemma, and he did this by guiding ACL2 through all the steps of the algebra for it. But the really cool thing you can do is you can say, well, look at the classical proof in one of the classical proofs of the Cauchy-Schwarz lemma. Take it, and then what you could do is you could say, so I want to do this big step, and what I do is I can handwrite out the algebra in the typical textbook fashion, and just notice there are these theorems I need about, there are these properties I have about inner product and other things like that, a couple, scalar vector multiplication, vector addition, and stuff like that. There's a handful of theorems I need about, and so what you do is you write, so you can just state the main result, and then you write down like 14 instantiations of theorems you know in your world, right? Which are just the steps you took in the hand derivation, right? And it goes through. It's really cool, right? So yes, being able to make a controlled introduction of facts from the ACL2's logical world into the SMT solver's world is great. Because you could just try telling it everything you know, but then we hit the exponential cliff problem. Right? That's a great way to push your solver across the exponential cliff. But you could say, these are the things that I believe to be relevant. And that worked quite well. Okay, let's see. How are we doing on time? Oh, yeah, okay. I'll try to wrap this up. So I'm going to do a couple of quick examples. Now we'll actually do hardware verification. So what we're going to get is that this is that phase lock loop that I told you about. And the interesting thing about it is that you can take a look at the two main control inputs to this are called V and C. And if you look at them on a plane, you find out that anything in the top blue moves to the right, anything in the bottom blue moves to the left. If it's on the wall, it heads, if it's on the wall here, it heads up. The wall there, it heads down. When it's in the red, it does something that's a little messy. But once it's in the green region, it kind of spirals to the yellow, which is the desired target. most of those steps are really pretty obvious, but the spiraling towards the target is complicated. It involves, do I have good proof of that? Okay, I don't have a good picture there. So what it involves in spiraling there is that there's this argument of saying, if I cross, if I basically have my phase error cross the origin, go from negative to positive, then the next time it crosses, it has to be closer in the target value of C than it had been before. And so this is the spiraling inward argument. Yeah, so you do a bunch of work, and the key thing is you have to prove this inequality, that for any h greater than or equal to 3, all this stuff holds. And we can prove this in Smtlink in about a minute, or in multiple pages of hand algebra to get through the whole thing. The full proof has about 75 lemmas, 10 discharged by Smtlink, and we expect a much simpler proof in the current version, but Yan keeps changing the interface, so she tells me soon she'll have a stable interface, and she can say, Mark, you can try it, see if you can simplify the proof. Another cool one, timed asynchronous circuit. So here's a really cool, simple asynchronous pipeline. The basic operation of this is that, for example, so every stage has an RS flip-flop indicating whether that stage is full or empty. And so if stage I is full, that would mean empty is false. And stage I plus 1, that means that its full signal is false. Then you're allowed to move a value from this stage to that one, and that's done because these two inputs to this NAND gate go low. The output of this middle NAND gate goes low, and that triggers the two RS latches to flip. So the two RS latches go from being in this state to this state. But the challenge, and it's a really cool, simple thing. It's simple, it's fast, it can be synthesized in standard cell libraries. Oh, and it generates a pulse here, which is just right for a latch or a flip-flop to move data between stages. That's kind of everything the asynchronous designer could hope for. But notice that either one of these two flipping changes the input to the NAND gate, which disables the signal. So there's a timing race. And so we have to show that the difference in the transition times on this RS and that RS has to be less than the delay to go through the inverters and NAND gate. There's a few other constraints. So how do we prove that? Well, we took a trace-based approach. A trace is a sequence of states. That totally makes sense, right? A state is a mapping from signal identifiers to signal values. Good enough, huh? And a component is a trace recognizer. So a component like the NAND gate looks at the sequence of the trace, and it's basically responsible for its output. A component may not stop its inputs from doing things. Right, so the environment can be nasty and bad. But a component says, if I see are the actions on this trace with respect to my output ones that I could have done? And if so, the component says good trace. If not, it says bad trace. And now a trace is recognized if all the components of the circuit recognize the trace. So we have very simple semantics for a circuit. Oh, and then timing constraints are just encoded by adding time to our state space, and then signals have an attribute of what time did they last change. And the rest is Abadia and Lamport's old-fashioned recipe for real time. Now, what's really cool about this is that once we've stated everything, what we find is that this is actually the whole proof tree. There are no more theorems. We've shown every single theorem in the proof tree for this. The blue ones are Smtlink ones. The other ones are done purely in ACL2 and are mostly inductions. So what's happening is that, in Smtlink 2.0, we don't have the ability to wait until you've got the inductive goal before Smtlink triggers. That should be here by the end of the year. Maybe even sooner, but what's happening right now is that you try the inductive theorem you want, it fails because there's some big and complicated inductive step it can't prove. You cut and paste that in as a lemma and tell it, use Smtlink. And then the lemma goes through, right? And so those are the blue lemmas that were all obtained by just trying their respective theorems, cutting and pasting the goal in. And that's all it took. So it handles all the details, and when you do this, proofs are cool and fun, right? Because I mean, all you do is it's pretty obvious starting on what are the main inductive results I need? Oh, I can formulate those. So I just state the main inductive theorems I want, and then I say, but what about this big messy pile of details? Throw it at the SMT solver. Okay, good, theorem done, great. Now here's another theorem I want. What do I do? Well, it's pretty obvious what the inductive theorem is. I state it. Then it produces a big pile of messy details. I say, I just throw it at the SMT solver, and the proofs go through. It's a lot of fun. So You say, you mean I don't have to figure out some clever way to get the rewriters? No, no, you don't. Cool. Okay, so to summarize this part then, we've integrated Z3 into ACL2. We could use other SMT solvers as well. Currently, the Python bindings of Z3, on the one hand, they kind of make me cringe because, I always have this kind of yucky feeling when I program in Python because, a semantics-free programming language. And so I say, and I'm claiming I know what the stuff does, and no one knows what Python does. But the flip side of it is that it does make it so that when you want to change something in the interface, it's really, really easy. So longer term, yes, we should have an SMT lib interface so that we actually have a very, very precise definition of what's happening at the boundary. Reflection and metaprogramming are really powerful mechanisms to transform a goal that the user wants to prove into a formula that the SMT solver can discharge. Gets rid of cuts out a whole lot, cut out the middleman, right? Get rid of all the junk in between. And support for user-defined data types means SMT is for more than just numbers. When we did Smtlink 1.0, common users in the ACL2 community said, but I don't have a numerical problem. If we look at verifying that time pipeline, yes, we're using the linear program solver in Z3, but more importantly, it's unwinding all these A-list and other data structures that we have for representing the circuit. And in fact, when we tried proving without it, you find you spend an enormous time amount in ACL2 just showing that your next state recognizer guarantees the presence of everything being properly defined in your A-list. Z3 just slices right through that. It's pretty cool. Okay, now, glitch hunting. These are going to be really fast now. So these are advertisements for people for the afternoon. This is some work we did, that Jan and I did with people at Oracle a few years ago. And this is because, basically you write a piece of RTL that says, that does like a conditional assignment. And the designer expects a multiplexer, but the synthesis engine does strange and wonderful things, oftentimes optimizations. It discovers it can fold the multiplexer in with other gates and things like that, which is just fine, except for I'm making a clock domain crossing. So what we can discover is that, this is being loaded on clock 1, but these signals change with respect to clock 2 at any arbitrary time. And so we can get some inopportune time. The synthesis engine could find a way where the signal coming in from the clock 2 domain is supposed to cancel itself out at the multiplexer, but the two paths took different lengths. And out pops a glitch. And then we have circuit failures. Okay. So, isn't this a solved problem? There are a handful of commercial companies, but this is being broadcast, so I will not name anybody in particular, but who claim to have tools for this. So our colleagues at Oracle tried running these, and most failed to run at all. They just crash. And the few that succeeded to run failed to find known glitches, right? And so now here's the big difference between what we've done and the commercial tools. You can look at this paper. We state the property we're proving. We have never been able to get a commercial vendor to say, so just exactly what property is it? Oh, we checked that there are no synthesis-induced glitches. Okay, what's your property? That's proprietary. We can't tell you. Just trust us, right? So, so first of all, we state what it is, and it works on real designs. So, two things. So, we've pushed this to design, working on modules of 200,000 gates over 150,000 flip-flops. But the other really cool thing I was talking with William about this yesterday. ACL2 has this package called SV, which is open source by the people at Centaur. They design x86s for embedded applications, which is a very comprehensive Verilog front end. So when William was saying, so what would we do if we wanted to use our tools here with Verilog? The first thing is you have to parse Verilog. The next thing is you have to figure out what it means, right? And the really awesome thing is, you throw this into the SV package, it builds common Lisp data structures for the whole thing, and it has an interpreter, which has been very carefully worked out to make sure it meets the Verilog specification. And one of the cool things, occasionally I've had questions about Verilogs, and you go to Stack Overflow, and you see the names of people at Centaur. Right? If you have some subtle question about Verilog semantics and you find it on Stack Overflow, you'll probably find Saul Swords or Jared Davis answering the question. These guys have really plunged into it. Now, so what would I do if I wanted to run some other tool and I wanted a Verilog front end? I would say, hey, I've got an open source tool that's really, really good. I'll just get everything and get all my data structures in commonness. Why? Because I would way rather deal with commonness than with Verilog, right? And now you say, but we're not doing commonness. You know, we want Haskell for Coq. I say, no problem. You want me to turn common Lisp into Haskell? I can do that. That's easy, right? You want me to turn Verilog into Haskell? Ooh, that's a massive headache. So if you want to get, so as you say, yeah, I want Verilog into Haskell, I'll give a strong advertisement. This open source package from Centaur is just awesome. And so, yeah, don't reinvent wheels. Okay, I'm going to skip this one, but this is kind of cool because it's an interesting global convergence problem which showed that using a different real arithmetic solver worked really well, right? So we solved the problem. We used Krassik's operator, which is an interval arithmetic verification algorithm, which is a class of things I haven't seen used much in the formal methods community. But the really cool thing is that we could solve this problem using state-of-the-art deep submicron transistor models. D-real and Z3 both time out on anything we try. We can do some pretty good examples. That's fun. Okay, good. Finally, future work. What am I planning today? Well, we're going to finish our current Smtlink. That's good. We're working on more circuits and robot stuff. In particular, one of the things that really underlies any of the stuff in continuous space is using automatic differentiation. An automatic differentiation is basically just a syntactic application of the chain rule. It's really cool. So you can just write down a term and you can ask what its derivatives are with respect to various things. And out they come, right? Or it doesn't give you the derivatives in symbolic form. It just gives you the function that evaluates that as well. That's pretty cool. But it's really lousy with fixed point algorithms. And given our time, if anybody says, why doesn't AD work with fixed point, then I'll just give you a cute example on a whiteboard this afternoon. So, but I believe that's because numerical analysts don't think in terms of fixed point algorithms. So if you say, wait a second, the reason my root finder it doesn't work with AD, the reason my optimizer doesn't work with AD, the reason my integrator doesn't work with AD is all because they're fixed point algorithms. And because there's weirdo things that happen because conceptually it's a fixed point, and so you went through an infinite sequence of statements, of iterations that got you to a real number. But now once you say, now that I understand that's what happened, I know how to deal with them. So I'd like to go that way. I want to integrate these interval verification algorithms into SMT framework. I mean, they have all kinds of verifiable things using floating point arithmetic. It's cool. You get rigorous proofs using floating point arithmetic for, like pretty much anything in a standard linear algebra package. So I'd love to have that. Okay, crazy things, some machine learning ideas, and starting a project on asking the question on can we synthesize an OS for the modern world. Okay. Had the opportunity to work with a whole bunch of different people on this. Good. So, any questions? Any more questions? I know we're running out of time. Yeah, so, any questions? Yes?
So I'm kind of curious about how this might, how it might adapt to other theorem provers, and I was wondering, like, which features of ACL2 did you think made it easy or hard? I think, like, being untyped made it more hard.
Okay, so the main thing I've seen when trying to look at, like Coq SMT or Isabelle Hall with Sledgehammer, the biggest thing that I've seen is that I have to admit, I'm not an expert in those theorem provers, and that's one of the things I'm really hoping to get feedback from people here. What I don't know is, can you do metaprogramming there? So that is, can I, in the middle of a proof, ask to see the quoted term for the thing I'm currently trying to prove? And can I manipulate that quoted term and give you return an equivalent or stronger quoted term and have the theorem prover be able to work forward with that? So, there's a bunch of infrastructure in ACL2 that supports that very comprehensively and very cleanly. I mean, one of the really awesome things about ACL2 is it's one of these things when you program in it, is you look through the stuff and you're trying to figure out how you do something. You look at it, and there's sometimes when you program in something and you say, everything's a hack. And other times you look at it and you say, why was it done that way? And you think it through, you go, that was really, really deeply thought out, right? It was done the right way. So I guess the big question is, what would it take to add metaprogramming to Hall or Coq or something like that? I don't see any fundamental reason it couldn't be put in. But I don't know enough about how the theorem provers are implemented to know. My guess is it's more than an afternoon project. Yes?
But Coq and Hall do have a form of metaprogramming, but usually when people use it, the result is that nobody can understand what the hell is happening in the proof.
Right.
Had that experience, like the system. Will
Right.
say,
So
yes,
what happens?
cool.
So what happens? Yeah. So actually, one of the things you'll see in my future work section, right? One of the first things I want to do is add counterexample generation for. For user-defined types. So right now we have a counterexample generator for the basic types. And when we were working on that timed asynchronous pipeline, one of the problems is you have exactly that. It fails and something went wrong, right? And now I can get that the SMT solver failed to discharge a goal. But why did it fail to discharge the goal? Well, the fantastic thing is the SMT solver came up with a model for the counterexample. So one of the things I did as we were working on that paper is I said, well, we're only using like a half dozen user-defined types. So, and this is the place where the Python interface is good. So I said, what I can do is I'll just quickly hack together a piece of code that just recursively walks through the Z3 generative model and produces a common Lisp term for the counterexample, right? So you could I could make it so that the Python code, in addition to saying it failed, would print out the common Lisp term for a counterexample, and then put the evaluator in an ACL2. And so then, and when you have that, there's this dramatic increase in productivity, because then I'm trying to prove some invariant, right? And I think I have the right invariant, and I get this counterexample, I drop it in, and it walks through, and it tells me exactly which clause of the invariant was failed in the post condition, right? Cool. And as soon as you see that, you say, okay, so this was my precondition, this is the thing, this is the pre-state, and this is the post-state, and this is the clause of the invariant that failed in the post-state. And you look at it for a second and say, oh, of course, that pre-state is absurd. I should never be there. Right? And what I need to do is I need to add this other clause to my invariant. So you find the invariant fairly quickly once you have counterexamples. So the fact that the SMT solver generates counterexamples is fantastic. Right now, as I say, it takes a little bit of manual hacking to bring them back in, but that's why it's high up on the future work list near term, is there's no reason we couldn't automatically generate those and bring them back in. Once you have those, life becomes a whole lot easier. In fact, that's a really great thing about this compared to purely symbolic methods, right? Getting counterexamples is great. Okay, more questions? Yeah.
So I had a question about the, if you look at, once you finish doing a proof using Smtlink and you have your proof script, how useful is it for someone to look and read that proof script? Because I guess, sometimes it could actually be helped by having some extraneous detail kind of omitted.
Right.
But
right. So actually, and that's what happened in any theorem prover, but in some sense, the really nice answer is you don't have to read my whole proof script. You need to read my top-level theorem statement, right? Because I can show you what my top-level theorem is or what the landmark theorems are, right? Because you have the assurance that these all actually are theorems, right? You don't need to know any other steps I took to prove them. You just need to say, I proved the following property. Also, what we get in our case is that I said, I have proven that the following predicate is an inductive invariant. That's the first thing you do. The next thing I can do is I can say, here's my initial state predicate, right? I can do a trivial proof that says any state that satisfies my inductive state predicate, my initial state predicate satisfies my inductive invariant, right? And I can also show that there exist states that satisfy my initial state predicate, so this isn't vacuous, right? And then I can show, what's the safety property you wanted? What's some property you want every place? I can show my inductive invariant implies that for everything. So I can actually have a set of very succinct theorems. Now, you have to believe this part that says this function is a model for the next state function of my circuit, right? Presently, we've handwritten those models. Now, if I were putting this into, if I were trying to do this in a place with a commercial design flow on their chips, I would say, hey, I want to build on top of that SV Verilog interface, and so rather than handwriting my models, I'm going to say, you can just load in this piece of Verilog code, right? And so my model corresponds with this piece of Verilog code, and these are the safety properties I've proven that holds, right?
Right. So in terms of,
and then those things can be very short and succinct.
Yeah. So if you just want to trust the final result, you don't have to understand.
Exactly.
But if you want to say, learn how to use the tool to prove something similar,
Right.
Can you get something useful out of reading someone else's script?
Correct.
Or are they
Right. Okay.
rational
That's correct.
proofs?
So basically, if I came here and you said, I want to prove the correctness of this crypto chip, right? So I could do all this. I say, here's my final proofs, right? Are you happy? And you go, well, I'm willing to fabricate that one, but I don't want to. I don't. We don't want you around here any longer. We want someone else to be able to do these proofs. So yeah, can they do these proofs? Yeah. So the question is, are the proofs readable?
Yeah.
And can you learn how to do it?
Yeah, like, is there any pedagogical value out of looking at someone's finished proof?
Oh, there's a huge value in being able to read proofs. Absolutely. And my experience with that has been that it's quite possible to, it is quite possible to write proofs that are really indecipherable by anybody else. Okay, right? That's not hard, right? And then the next question is, can you write literate proofs? So can you write a proof? And my own experience has been that, and I'm going to claim that that's going to probably hold in any theorem proof you use, is actually sort of, it's a second phase. First I get the proof to work, right? And then I go back to say, can I explain this proof to somebody? Oftentimes that's adding loads of comments in places, right? Why did I do this? Because I ran into this problem, right? And then other times it's why did I do this? Well, because I didn't know what I was doing as I did that, and I didn't realize that the following property held, and that was the key one I need. And so I was kind of going down a blind alley, except for I sort of used a little bit in it. Oh, wait a second, I could throw out a whole bunch of that and just go straight to the key thing. Right? So, but I don't think that's really different in any of this. The good thing is that there's some pieces of this that we get that by moving a lot of the tedium into the SMT solver, theorems usually, and I look at the proof tree that we had, for example, for the asynchronous pipeline. That proof tree, you walk through what the different goals are, what the different theorems are, they totally make sense. That if I were to explain to you, if you walk through the proof tree and say, why did you need this theorem? You wouldn't say, that totally surprises me, right? I mean, most of they're building inductively over the trace, and they're building inductively because we prove things for an n-stage pipeline or ring, right? And so there's an induction over the trace, and there's an induction over the structure. And if you look through the theorems, that's what they are.
Okay, so it sounds like your answer is that you can make explanatory proofs with some extra work.
Right, but I don't think that's any different than writing code, right? You can write code that's impenetrable, or you can write code that's self-explanatory, and the second one takes more work, right? Yeah. And we've all seen way too much code that's impenetrable. Okay, other questions?
Well, we should probably wrap up in here,
Okay.
but we're going to be in our meeting for the rest of the morning and for the afternoon. So,
Oh, that's great. Well, the real fun one now is that
I scheduled time with Aaron.
Canada just contributed
I think it'd be really useful.
about
You're invited.
7 years ago.
Yeah, I saw.
I have in my desk
family visiting.
I wasn't sure if I should
By like be on set.
Yeah, up to you.
I just don't spend a lot of
Yeah.
Covers from your